Welcome everyone to the week 4 sample assignment tutorial session of Galois theory MA70. We will discuss some questions related to week 4 assignment, which are like non-star non-blue questions. So let's begin. Let G be a finite multiplicative abelian group of order n, and let mu G is equal to the product of all the elements x in G. So this is some notation, so let's write it down. G be a group, so it is finite, and this is a group. Okay, yeah, and G is an abelian group with respect to multiplication. Okay, and order of G is given to be n. Let mu G is equal to the product of all the elements of G. Okay, it's just that it is just a notation. If we have some other group, we may still write mu of that group, like mu of H or something like that. Anyway, so this is defined to be the product of all the elements of G. And okay, so these are notations. G2 is a set which contains all the elements x of G such that x square is equal to 1, and this superscript on left 2G is equal to all the elements x in, sorry, we may just write x square such that x belongs to G. So all the elements, just square it up and just consider a set of distinct elements. It's not like if we have, for example, G to be 1 and minus 1, then G2 will be just 1 because square of these two elements will be 1. So we are not going to consider kind of a multi-set with square of these elements to be something different. We'll consider it same only. Okay, is that okay? And similarly, if we have to write G2 in this case, what will it be? What will it be? G2, if G is this?
1 and minus 1.
Exactly. So this will be 1 and minus 1. So yeah, some kind of an example. But anyway, we are not in this case. Okay, let's see. So this is the given data, basically definitions. Prove that G2 and this 2G are subgroups of G and mu G is equal to mu G2. Okay, let's see. So first part is, these are groups. So these are subgroups of G. So let's consider G2. So one thing, so to show G2 and 2G are subgroups of the group G. Okay, so let's start with this G2. So how shall I start? So if you want to prove that this is a subgroup, what should I prove?
Is it given to us that G is finite?
Yeah.
Then we can just show that for every x and y, xy is in the group.
Exactly. So since G is finite, inverse is also an element, like we can write it down in that term. So okay, so xy. So basically, if it is finite, then it is some power of other element. So that's why we can consider, like, let's say z square or something like that. So when it is finite, we don't need to really do this for inverse. So okay, let so for example, when you consider z, that is an infinite set. So minus 1 cannot be written as some, let's say some, so for example if we take 1, so it is generated by generated by 1, but we cannot write minus 1 as some positive power of this. So that's why we cannot do it in infinite fields, but here we can do that. So let's say xy belongs to G2, then this implies
xy into xy will be equal to, because it's abelian, will be yx into xy, which will be x square is 1 because x is in G2, and that will leave y square, and y square is 1 because y is in G2, and thus we can come to the conclusion that xy is also in G2.
Exactly. So as you said, xy belongs to G2. This implies x square is equal to 1 because G2 has the property that all the elements, by definition, G2 contains all the elements of G such that its square is 1. So xy belongs to G2, that means x square is equal to 1 and y square is equal to 1. So if we consider xy square, then we can write it down to be x square y square because G is abelian. G is abelian, so every element, every two element commute here. So G is abelian, so we have x square y square. This is equal to, since x square is 1 and y square is 1, this is equal to 1. Very good. So this implies, since square turns out to be 1, this implies xy, and xy belongs to G, of course, xy belongs to G2. So this is a subset of G. This implies the product xy will belong to G because G is a group. So xy will belong to G, and because of that, and xy belongs to G and xy square is equal to 1, so this means xy belongs to G2. Okay, so this G2 is a subgroup of G. Very good. So let's try with this. So again, this is G is a finite set, finite group. We can again consider just two elements of 2G. Now if xy belongs to 2G, which is equal to what? Which is equal to all the elements. Say, okay, if I write it here, don't get confused. So 2G is given to be the set of elements such that x square, sorry. So this is equal to x square where x belongs to G. So every element of 2G is some square of is a square of some element of G. So that means if xy belongs to G, this implies there exists AB belongs to G such that x is equal to a square and y is equal to b square, because the elements of G2 the elements of G2 look like as square of some element of G. So that means xy will be something, yeah.
Because G is finite, can we say that G can be written as 2G, like 2G can be written as some product of cyclic subgroups, and these product of cyclic subgroups must be of the form A square cross B square cross C square and so on and so forth.
I didn't get it. So you are saying 2G
can be written as a product of cyclic subgroups of the form product of A square, like a cyclic subgroup A square.
But we don't know 2G is a subgroup right now.
Oh, right. Okay. Yeah. Sorry,
Yeah. We don't. We are proving this. Okay. Yeah. So it's not good to use fundamental theorem of abelian groups maybe you were using that, but anyway. So
Yeah.
this is a set right now. So let's see, because now you know that so there exists AB belongs to G such that x is equal to a square and y is equal to b square. Now we are interested in xy, product xy. We want to prove that xy belongs to 2G. So we should be able to write it in in some as a square of some element of G. So let's see what it is. So since xy is given by this, so we have AB square. So that means, so now since a comma b belongs to G, we have, because G is a group, the product will be there, so we don't need to worry here. So this implies xy is equal to AB square, where AB belongs to G, and this means xy belongs to 2G, right? Thus, since xy are the arbitrary elements of 2G, this this is true for every element. So this is a subgroup of G. Is that okay? Any doubt? Any doubt? Okay, great. Okay, so first part is done, first part of A. Now we have to prove that mu G is equal to mu G2. Let's see.
Mu,
Yeah.
what is the definition of mu? Finite product of the element of G.
Not finite product. G is given to be a finite group, so as per the definition, it is just the product of elements of G. It is given in the question itself. So yeah,
Okay.
G is finite, so yeah, this is a finite product with all the elements of G. So X belongs to G. Oh yeah, we want to show that this is equal to this. So what is mu G? Mu G is product X belongs to G X. So okay, what can I do? Okay, the thing, what is G2? G2 is all the elements of G2. So as I said, this is from the definition itself. So mu of any group is defined to be the product of all the elements of this group. Okay, this is from the definition, so we can write mu G2 like this also. Okay, so it's not unknown here. Since we have proved that G2 is a subgroup, so this is a group, and we can write because of that definition now. Okay, so what does this mean? This means, now what is G2? G2 is all the elements of G such that x square is equal to 1, right? So what can I do? I can write it to be x belongs to G such that x square is equal to 1. So all the elements, so this is what we need to prove. This is equal to this, right? So basically we need to shrink this product to just the elements which are whose square is 1. Okay, so can you suggest anything? So let's try one thing. So we need to prove this. So I'll just, okay. So, yeah, so I'm working on this line. So okay, so what we can do, as we need this part, we can try to separate this as this x square is equal to 1 x into product all those elements of G which does not satisfy this property. Is that okay? This is like uh, all the cases are there. So it's like either x square is so any element of G will satisfy one of the condition, either x square is equal to 1 or x square is not equal to 1. So we have separated it out. So what we really need to prove, since we need to prove that this is the only part which to which mu g is equal. So this means this part should not play any role. That means this is equal to 1, right? If we can prove that this is equal to 1, then we are done, right? So this is the task. So this we need to prove. Can you suggest something? What can we do here? Anyone?
Ma'am,
Yeah.
x square is not equals to be 1 and g is a multiplicative group. So x square not equals to 1 implies that x must be identity because by
Oh. No. This is a multiplicative group, so it could be like, for example, you take ZP cross, and let's say P to be 5, or maybe bigger, let's say 7. Okay, then we have like 0, not 0, because I have taken cross, so it's like units. So that is 1, 2, 3, 4, 5, 6. Because this is prime, I can, like, this is mod 7, and 7 is prime, so the elements will look like 1, 2, 3, 4, 5, 6. So I have just picked the representatives. Yeah. Okay. Yeah. Right. Right. Others. So yeah, as I was saying, so minus 1 is this. Okay, so 6 is equal to minus 1, because 6 mod 7, you can write it to be 6 minus 7, and that is like minus 1. Okay, so but other elements have some bigger order, and this is a multiplicative group, abelian, everything is there. So there are elements which have order bigger than 2, because this is saying, since this is a finite group, this is just saying that the elements which have order more than 2, x square is not equal to 1, that means there is some bigger power which is equal to 1 and not the lesser ones, like the order is bigger than 2. Is that okay? So there are elements in this set. Is that okay? I can explain again, or have I answered your question? I'm not sure.
yes, ma'am.
Okay, great. So yeah, as Adarsh has typed in his message, so he said, in this case, when x square is not equal to 1, then any element which satisfy this property, its inverse will be distinct. So what does he mean? So let's take x belongs to G. Okay, if, so I can write in this sense also, if x is equal to x inverse, this implies what? X square, I can just multiply by x inverse, I can multiply by x, so this will be x square is equal to 1. Since G is a group, I can multiply by x in x, and I can get this. Okay, so whenever so this is even if and only if case. No. Right, yeah, this is okay. So we have this property. So that means if x square is not equal to 1, then x is not equal to x inverse, because if it is, then x square has to be 1, which is a contradiction. So we have this condition. So and also we know that order of x is same as order of x inverse. So this implies x square is not equal to 1. This implies, so x square is not equal to 1 implies not minus x inverse square is not equal to 1 also. So with this condition, what we got, yeah, so we got here in this part every element will be in pairs. Okay, so if x is there, then x inverse is also there, and these will be so these are not equal. So this is the condition we have. Okay, so every element will exist in pairs, So that means you have product like x inverse, some other element, let's say y inverse, and so on. So when you do the product, you will just get identity up to and so on identity. So this product will be just 1, and we are done.
Ma'am,
Yeah.
also conversely, I mean, not conversely, like similarly, using fundamental theorem of finite abelian groups, I can say that each group can be represented as a product of cyclic subgroups, right? And of prime power. So in each of these subgroups, I can observe that there will only be 2 elements that will satisfy x square is equal to 1. And the rest of them, I can use Wilson's theorem. And the only thing that will be left, so using Wilson's theorem, there will be minus 1. And the only
Why
elements is
minus
E and,
1? No.
sorry?
You have prime powers, not just prime numbers. So Wilson's theorem, it's like p minus 1 factorial. So this is equal to y minus 1 mod p. So you are having just zp here. If you consider this like product of elements or something like that, you are talking about zp only, not zp raised to power something. Because when we
Right.
if you use fundamental theorem, then it is like some powers. So this is isomorphic to z mod p1 raised to power r1z to and so on. There are some powers, so we cannot say directly that we can use this.
Okay.
Yeah. Okay. Anyway, nice try. So, yeah, is that clear? So why mu g is equal to mu g2? So what we did? So, okay, too much chaos. So what we did, we just wrote this product as product of elements which satisfy the property that x square is equal to 1 and x square is not equal to 1. So we separated it out, and from this we keep the first part as it is. From the second one, we know that every element will exist in pairs. So this is like this, y into y inverse, everything will be distinct, and up to and so on z. Again, I should write in some, let's say x1 into x1 inverse, any. So this is a finite product. It will stop somewhere where x size belongs to g. Okay. And yeah, these are not equal, so this is okay here. And what we got from this part, yeah, yes, so this is just 1, and we got that this is mu g2. Okay. Let's move to the second part then. So we proved that mu g is equal to mu g2. So it's like product of all the elements is same as just doing the product of elements whose square is 1 in a group. Now second part says, if G is a subgroup of multiplicative group K cross of a field K, and if minus 1 belongs to G, then mu G is equal to minus 1 is equal to minus 1 raised to power n minus 2 n by 2 mu 2G. So let's write it down. What does this say? Okay. Part B. G is given. So as there is, we already know G is a finite multiplicative abelian group of order n. So this is a finite group, and this is a finite multiplicative abelian group of order n. So this is also the condition for part B, because this assumption has been done for the whole question. So G is a subgroup of, so multiplicative subgroup of, so this is a notation for subgroup which I am using, subgroup of K cross, so multiplicative subgroup. We don't know if K is finite or not, but we do know that G is a finite subgroup, okay, where K is a field. Maybe infinite. We don't know about its finiteness or infiniteness. Okay, so this is the condition we know. Now, okay, it is also given that -1 belongs to G. So there is one more condition. We already know 1 will be there because G is a subgroup. So K star has multiplicative identity to be 1. So G will contain 1. But we have this extra condition that additive inverse of 1, that is -1, is also in G. That is not required to be there to become a multiplicative subgroup. But we have this extra condition. Now to show mu G is equal to -1 is equal to -1 raised to power n by 2 and mu G 2G. So this is different one. This is the product of squares of elements. Okay, so let's see. Okay, first let's see if we can do for mu G is equal to -1. Okay, if we can prove this. So we have proved that mu G is equal to mu G2. This is from part A. So that means this is a product of all the elements of G such that x square is equal to 1. So that is x, right? Now, can you tell me how can I say that this is equal to -1? What can I write here? So this is a product of all the elements of G such that x square is equal to 1. So first thing, what do we know about G? So like G is a multiplicative subgroup of K cross and K is a field. That is a very good thing we know in this question.
Now G is cyclic, finite cyclic.
Exactly, yeah.
And so it is isomorphic to Z mod NZ.
Right, very good.
Then since
As
we need
addition.
we so product we want to do product will be -1.
Yeah, right. So yeah, this is exactly, so this is cyclic. We have proved that this in class. So this is isomorphic to Z mod NZ as a group isomorphism. Z mod NZ with addition, operation addition. Addition means addition modulo n. Right, so this will be isomorphic to this. And what we know, so this condition in Z mod NZ is like what? In Z mod NZ, x square is equal to 1 is like 2x. So the operation is addition. X square means you are operating it twice, like x into x, and now into multiplication is like addition here. So 2x is equal to, and you will have identity to be 0. Oh, what am I writing? 1 second. Oh, okay. So this is based on the map. So yeah, I should not say like this. So yeah. Yeah, was that right? So if you take, yeah, 2x is equal to 0, right. So 2x is equal to 0, and so x will x could be what shall I say, -1. Yeah, so it's like x, right, okay, it's fine. So x is equal to 0 or or the other one could be like whatever x by 2, right? X by 2 means, oh, there should exist that. Oh right, -1 is given to be in G, so there, so x by 2 will exist. Okay, yeah, this is one way to do that. I mean, so what she said, you consider, since we know that G is a finite subgroup of the multiplicative group uh, of a field, that is K cross, it has to be a cyclic subgroup, cyclic subgroup of K star, which we did in the class, in the lectures. So that means G can be think of as an like G. There is an isomorphism between G and Z mod nz comma plus, like with operation addition modulo n. So we can define isomorphism, and isomorphism will be like, all the, you can think of all the elements like generator wise, you can define this mapping. So from that you will get this data. Z mod nz is in Z mod nz, x square is equal to 1 will be thought of as 2x is equal to 0, because this is additive identity. This is the this is x dot x, so the operation will be now plus, so this will be 2x is equal to 0. Then either x could be 0 or x by 2, because when you go mod, still I am not saying right. 2x. So in Z mod nz, when
Ma'am,
will the 2x, yeah, that will be like, so since -1 is there, -1 belongs to, so what does -1 mean in Z mod pz, in Z mod nz, in addition? So that will be half, actually, half. So x will be 0 comma n by 2. Yeah, this is the right one. Yeah, this will be n by 2, because -1 exists in G, so the element n by 2 is defined. So okay, let me clear this up. So -1 belongs to G. This implies, so you have -1 square to be 1, and so you have an element of order 2, so this implies 2 divides order of G. So the order of G will be a even number, so that means n by 2 will be defined. Is that okay? I'll give another explanation for this part also, but is this okay?
Yes.
Okay, so yeah, this is one explanation, and that is good. But we can see in another way also. So you have x square is equal to 1. In so if you just think of this in the field, so G is a subgroup of K cross, where K is a field, right? So K is a field, that means we can think of, so all the elements of G are coming from the field itself. Okay, so we know that in the field x square minus 1, any polynomial will have at most 2 roots, 2 zeros, right? So any polynomial will have at most degree of that polynomial zeros, right? And the elements are coming from the field. So G is a subgroup of K cross, so we are not adding elements, so we will still have this condition for G, right? Because x square minus 1 is a equation in K cross with the coefficients here, right? Now since this can have at most 2 zeros, so we already have 2 roots here in G. So we are not going to have more than this. So that means this will be equal to just 1 into minus 1, because we don't have other elements with the condition that x square is equal to 1. Not even in G. so not in K cross, so that means not in G also. And since minus 1 belongs to G, we have 1 into minus 1 here. Is that okay? So this is something which we are doing anyway, thinking of cyclic here. But yeah. If we construct a set S, so Adarsh has written something, I'm just reading this up. If we construct a set S such that only one of x or minus 1 belong to S, since they are distinct, why they are distinct? Okay, x or minus x belong to S, since they are distinct, we get two product, which gives I didn't get your comment. Can you unmute and speak? Are you talking about this question only? This part? If we construct a set S such that only one of x or minus x belong to S, why x and minus s are different? But do we need this much to do for this part? Like we just use this property that in the field x square minus 1 will have at most two zeros, and we use that, and we are done. Okay. Okay, so yeah, is that okay? This part now? This is equal to minus 1 as required. Let's prove the other part. So other part is, we need to prove that this is also minus 1. Minus 1 raised to power n minus n by 2 mu g2 2g. So this is what? Minus 1 raised to power n by 2 mu 2g means the product of elements. So yeah, there is, so just be cautious here. So you have let me write like this. So y belongs to 2g. Okay, so why I'm writing like this, don't think that this is same as x square where x belongs to g. This product and the product this one, these are different. Can anyone tell me why? Because you know that g2 is all the elements x square where x belongs to g. So I'm saying these two products need not be equal every time.
Certain numbers could get repeated.
Yeah, exactly, very good. So what could happen, you might have for example I don't know, maybe minus 1 and let's say okay, so for example you have 1 minus 1 here only in G, then 2G is just 1. You just take the set with the elements squared. So both the elements will square to just 1. So we will get just product 1. Okay, so this means here this won't create any problem because this is just 1, so product of ones will be just 1. But for example, if you have something like let's say x y, where x square y square is equal to minus 1, let's say this, then in the set this, you can have more than these elements. Let's say 1 is also there. Okay, don't think this is a group or something, but at least some example. So when you square it up, you will just get this. But when you take this product of x belongs to g, x square, so you will have 1. Now square of x is minus 1, square of minus 1 is minus 1. So you will get here 1. But in this product, the product of 2g elements of 2g, it says you just take all the elements which are distinctly you are getting from squaring the elements of G. So that is just 1 into minus 1, which we wrote it down here also.
As an example, you could take one
Yeah.
I, one minus one, and minus I.
Yeah, exactly. So you just add one more element. So x and y are like I and minus I, because the squares is minus 1. So you take 1 I minus 1 and minus 1. So yeah, exactly, very good. So we can take this example. We know that this is a group, so there's no issue. So you have 1 into minus 1 into I into minus I, like elements 1 minus I. So let's erase this also. The condition is same. So you have I and minus I. Then when you do square, so you will get 1 square is 1, minus 1 square is 1, I square is minus 1, and minus I square is minus 1. So you will get just this. But when you do the product, you will get 1 is 1 into 1 into minus 1 into minus 1. Every element will be there with the square. Okay, even though it is same or different, we don't care, because we are in the case that you are taking x square where x belongs to G. But here you are just taking squares as a set, so that means this is just minus 1. So this is different, so don't be confused by that. Yeah. So let's see, what do we have? Minus 1 raised to power n by 2. Okay, now just be cautious here. You take this product. Now you know that mu 2G, so okay, mu let's say h, we know that this will be equal to h2. So here also this will be equal to what? Because this is a group, we have proved that this is a group, so this means this will be equal to 2G2, right? In the first part we have proved that for any group, finite group, mu G with abelian everything there, mu G is equal to mu G2, right? In subscript. That means taking the product of all the elements of a finite group, it's a finite abelian group multiplicative. It's same as multiplying just the elements of the group with the property that its square is 1. So let's use this here. So you have y belongs to 2G, and y square is equal to 1. We just added this condition. We have proved that in first part A. Okay, so yeah, so you have minus 1 raised to power n by 2. Now let's get down to G now. Now you will have, so I'll just replace y by x square, because all the elements of 2G looks like square of the elements of G. So I'm not doing x here and square there, I'm just writing x square belongs to 2G, and I'll just write x square, and here what will it become? X raised to power 4 is equal to 1. Is that clear?
Yes.
Okay, great. So let's keep this here only. Now let's split this in some cases. So okay, why am I doing it? So let me explain that. So you have this condition x raised to power 4 is equal to 1. Now we need to find like fourth roots of unity in the group G, like this. So we are interested in that part. So again, since G is a, so just consider this, since K is a field, x raised to power 4 minus 1 will have at most 4 roots in K. Okay, in K. So and so in G. Okay, so K cross is always there. We are not interested in 0, but that's okay. Right. So so in G also we have just the condition that it can at most have 4 roots. And what does that mean? What will be the roots? Roots will be what? So can I write this? Because this can be factorized even in G, because -1 is there in G. Okay, this means roots of G. So this even I can write K here for simplicity. Even I can think of this in G. That will not be a good notation to write, but okay. So this is like zeros of set of zeros of x raised to power 4 minus 1 in K. So in the field K, what are all the zeros of x raised to power 4 minus 1? This is the set of that. Now this means the roots are 1 and -1, and because this will have just 2 roots and these 2 roots are there. So we have this, that's okay. Now what does this mean? This means all the points with the property that x square is equal to -1. So like x square plus 1 is equal to 0, that means x square is equal to -1. That might not be a good notation, but let me explain. So zeros, okay, I can even write roots because this is now equation. Roots of x square is equal to -1. Solutions of x square is equal to -1. Okay. So in K, now what could happen? Either roots will exist here or it might not, because it could be there in the bigger field but not here. For example, you just take this set 1 and -1 to be G, then the roots of x square is equal to -1 is not there. So you have to extend it to some bigger field, for example 1 minus 1 iota minus iota. So it could happen that this does not have any root here of this equation, right? So when will it happen? When will it happen? So can you tell me when will it happen? Roots will be there or not? What is this condition? We can separate it. So roots of x square is equal to -1 is not in K, means 4 does not divide n. Is that okay? Or let's say, okay, let me write it down in this sense. Just separate it in two cases. 4 divides K or 4 does not divide K. You can explain what we are doing. So if 4 divides K, what does this mean? This means roots, okay, so 4 divides n, what does this mean? You have, so by Lagrange's theorem, not Lagrange's, I want to say since, or you can keep it as an exercise also. Since G is cyclic, there exists an element of order 4. Is that okay? Because 4 divides n, so where order of G is equal to n. So G has n many elements and G is cyclic and 4 divides n. That means since G is cyclic, we can prove that there exists an element of order 4. That can be done easily, like you just think G to be like generated by A, and then you can prove that A raised to power n by, for example, 4. When you take this will be equal to identity and not lesser number. So this can be proved. Okay, just think about this. So G is cyclic, so there exists an element of order 4. So that means there exists an element, say y, okay, So that means y raised to power 4 is equal to 1. And this cannot be 1 or minus 1, because if it is 1 or minus 1, then the square will be just 1. So that means this has order 4. So this has to be some root of x square is equal to minus 1. Is that clear? So we can just think of the cyclic group G, then it will have just one this, so even more in particular, furthermore, order of what is the notation, I guess mu, I don't remember. So number of elements of order 4, do you know how many elements will be there in a cyclic group for any order if it divides?
Exactly that number.
That number?
Order.
Oh, no, it is 5. We are not
Oh,
saying
sorry.
at most 4. So at most 4 will be 4, but it will be 5 of that element. So this is Euler-Toshian function. Yeah, 5 of n by 4, is it? It's just 5 of 4. The elements will look like this: n by 4, a raised to power k n by 4, where GCD of k and 4 is equal to 1. Yeah. So the elements will look like this. So that's why this will be phi of 4. So that is some we know already. And phi of 4 is what? Phi of 4 is equal to 2. So there will be 2 elements of order 4 in this group G. Okay. So because of that, now let's come to our situation. The situation says that you have to find this product minus 1 raised to power n by 2 mu of 2g, which has become now product x square belongs to g, and x raised to power 4 is equal to 1. Now if 4 divides, that means you have all 4 elements here. Okay, all the 4 elements are there, so the product will be what? 1. Oh, okay, one more thing, we are talking about this set square. Okay, so as actually we did 1 minus 1 iota minus iota will be this set, but anyway 1 minus 1, and you will have what? You will have the roots. So y square is equal to minus 1 and y square is equal to 1. This will be the elements of order 2. This will be the elements of order 4, which will satisfy this. So the square will be just minus 1. So let's say some element y and its inverse actually. So these are elements of order 4 which exist because 4 divides n. We did already this. So we have these elements as variety of x raised to power 4 is equal to 1 in even the field, but I should not write G because this is the notation completely for field, but this is also in G also. So this is in G also. Okay. So this is this set. Now what you need to do, you need to square it up and take the product with distinct elements to be here. So when you do square here, so square of this, so when you do square, what will you get? You will get 1 and so minus 1, so square of this, square, I'm doing square of this will be 1, square of this will be 1, square of this, y square is, we know that this is minus 1, so this is minus 1 and this is minus 1. So as a set we get 1 into minus 1, so this will be 1 into minus 1. One more thing, since 4 divides n, this implies n by 2 is even, because it is a multiple of 4. When you just take the when you just divide by 2, you will still get it is a product of 2. So it is a multiple of 2, sorry. So n by 2 is even. So that means this power will be just 1 into this is like minus 1. So you will get minus 1. Is that okay? So what we did here, we need to find this product. So we have written it down to be in the form using part A. So it's just all the elements with the square to be 1, and here it will become the x raised to power 4 to be 1, and from the field thing, and we know that this will have just at most 4 elements, and since 4 divides n, it will have these 4 elements in the group G. Okay, so these 4 elements, we just take the square of these elements, and from the condition x raised to power 4 equals to 1, and the condition like this will become y square is equal to minus 1 and y square is equal to 1. So there will be 2 elements whose square is 1, and there will be 2 elements whose square is minus 1. So then you again square it up, it will become 1. So the order of these 2 elements is 4. So you got in the set x square, the set x square 1. So so this is 2g, not right. So this is 2g, x square belongs to 2g. So when you take this set, then you will get just 1 comma minus 1. So we can write it down here, and from the condition that 4 divides n, we know n by 2 is even. So minus 1 raised to power even number is 1, and this product will just give minus 1. So whole product will be just minus 1. Is that clear? I'm a bit messy, but I'll try to keep it separate. And anyway, so let's take the other case which says 4 does not divide n. So what will happen here? You don't have any element of order 4 because 4 does not divide n. So this implies G does not have any element of order 4. So x raised to power 4, so elements of G which satisfy, we don't know about the bigger field K, will it have the order 4 elements or not, but at least in G we don't have this condition. Okay, like G is just a subgroup of K cross. It could be like there could be elements of order 4 in the bigger K cross, right? But we are not concerned about that. So we only know that G does not have any element of order 4. So elements of G which satisfy x raised to power 4 minus 1 will be just 1 and minus 1. You just have 2 elements. It does not have these y and y inverses in G. So now again we are concerned about this product mu of 2g, which is equal to minus 1 raised to power n by 2. Now the product again says x square belongs to 2g, x raised to power 4 is equal to 1, and you have x square. So again what will you do? You have this set to be concerned about. These are x, so x square will be, so when you do square, you will just get 1 square. So as a set, when you square it up, you will just get 1. So there will be just 1 element. So here minus 1 raised to power n by 2, and you will get just 1. And now what is n? N 4 does not divide n. This implies when you do n by 2, this will be odd. Exactly. So this is odd, so minus 1 raised to power n by 2 is
minus
odd.
1.
Yeah. Is that clear?
Yes.
Okay.
Ma'am,
Yeah.
I have got my connection lost due to network issue. I have not clearly understand what are you give as a exercise. Since G is a cyclic, there must exist an element of order 4. Is that
Yeah, so with this condition, assuming this condition, like, so basically it's a general fact, if G is cyclic, then for every divisor of, so G is a finite cyclic group of order n, then for every divisor of m there will exist some element of that divisor of order d, and exactly it will have phi of d elements in the group itself. So
Set of generators. Five.
a set of generators of uh, which
Five. Set of generators mean order, if order of the group is n, phi of n means those number whose co-prime with the n.
exactly.
Uh, so
Yeah, for n
uh,
it is this case, so I can write more precisely. So this is the general fact which we are using. So okay, so this says uh, if G is finite cyclic group of order n, then for every divisor, or maybe for each divisor, d, there exist exactly phi of d elements of order d in G. So of order d there will exist phi d elements in the group. So yeah, this is something you can prove this. Just think of G to be like generated by A, then you can just consider all the elements of, like, for example, for 4 it is this. So for example D, you can do this. So A raised to power n by d, you consider that, or and you take all the k where k and d gcd of these is equal to 0, then order of this element will be equal to exactly d, because you know that a raised to power n by d, when you power it to d, then you will just get a raised to power n, which is equal to 1, because G is a group of order n. So that can be proved like this. Is that okay?
yes, sir.
Okay. Okay, so still we are not complete with the question. So there is more which has been asked. So, yeah. Okay. So B1, yeah, let me. So, okay, we need this now. So now it is given if p is a prime number, so we have to deduce this. So assuming this, so we have proved a and b. So using this, we need to prove b1 and b2. Actually, Wilson's theorem we need to prove. So now what? Okay, so to do this, what choice of G I can use? G and K star, K cross. What do you suggest? Think here, what we need here, we need -1 mod p, so -1 looks here, so that means we should be able to so this factorial is also a product, like 1 into 2 into up to and so on, p minus 1. So mu of G, we are thinking the product to be 1 2 3 up to and so on, p minus 1. So what we are thinking, and mu of G is what? Fp cross, exactly. So what we can, so as I said, this is p minus 1 factorial. So mu of G is what? Product of elements of G. So what we are thinking, if we take G to be Zp cross, so so we know that Kp, Zp is a field, since P is prime, because P is given to be prime. So Zp is a field. So this will be Zp is a field. So we can take. So just think this to be K. Okay. So we have taken G to be whole K cross, right? So this is whole K cross. So take G to be equal to ZP cross, and where ZP is K. Okay, so you have taken G to be the full multiplicative group, ZP cross. Then from the, since mu of G is also note that -1 is there. We have all the conditions. -1 belongs to G. Since -1 belongs to G, that is equal to what? ZP cross, and ZP cross has -1. What is that? That is this is like P minus 1. So you know that ZP cross is what? 1, 2 up to and so on, P minus 1 mod P. So P minus 1 is -1 mod P. So P this -1 is just P minus 1. So it is there in G. Okay, so this implies by B mu of G is equal to -1. And what is mu of G? Mu of G is 1 into 2 into up to and so on, P minus 1. Again, mod P is always there because we are in mod P, ZP star, so that is mod P. So this is equal to -1 mod P. So this product is P minus 1 factorial. So -1. So that we needed, which is Wilson's theorem. Is that okay? Is that okay? If not, just let me know, I'll explain again.
Just 1 second.
Yeah.
Ma'am,
Yeah.
if we take K to be polynomial ring,
Sorry. If we take K to be
polynomial ring, FPX.
K to be polynomial ring FPX. Not ring. We in the condition we have that K should be a field. Maybe we can take square bracket. Sorry, this one.
I put this one. How to conclude K must to be finite?
Uh,
From B.
so we are not saying K is finite. G is, so it's like we have proved a big equation, like we have proved in general, like G is a subgroup. Okay, so this is the condition. G is a subgroup of a multiplicative group K star of a where K is a field, and G is a finite group with elements with number of elements n. So this was the question. So we have, yeah. So this condition is always there. G is finite multiplicative abelian group of order n. Now in the part we have proved that if G is with this condition, G is with this condition, G is a multiplicative, G is a subgroup of multiplicative group K star of a field K, and if -1 belongs to G, then we have this condition. So this is true for any field K. If this condition is satisfied for any field K, then we have mu G is equal to -1. We have no restriction on K, but this should satisfy. G should be a subgroup of, G should be a finite subgroup because G is finite. G is a finite multiplicative subgroup of order n of a multiplicative group K star where K is a field and -1 belongs to G. So this is true in general. If this is the case, then mu G is equal to -1. Now if we can choose some G and K star of our choice which satisfies this condition that G is a subgroup of multiplicative group K star, where K is something which we are also picking because we have this choice. We are just putting some G and K of our choice so that -1 is also in G. Then we have this condition mu G is equal to -1. So we are not saying in the condition that K is finite, but we are choosing K to be something like that, which we can do because If we say, so we have a general statement, we are just keeping some G or K of our choice, because that is there. Like if we choose something like that, then they should satisfy. Is that okay? So it's like, for example, Lagrange's theorem says that G is a finite group, then of any order, order of any element will divide the order of the group, right? So now you can choose G to be ZP, and then you can say that order of any element of ZP will divide P. So it's like that. We are just choosing G and K to be such that which satisfy these two conditions, that G is a subgroup of K star and -1 belongs to G. Is that okay? Okay.
Yes.
Okay, great. Yeah, it's this might be confusing, but yeah, we are just picking it up, and that we have the choice we have, of course. Okay, yeah, but good question. Okay, so this is done. Now second part, if P is not equal to 2 is a prime number, then the element -1 is a square of ZP if and only if P is equal to 1 mod 4. Actually, this is a very good statement. Even you can prove that there are infinitely many primes of order 1 mod 4. So like the proof, this Euclid's proof of prime of infinitely many prime numbers. So do you know what is the proof? So how what is Euclid's proof to prove that there are infinitely
Consider
many?
that there are finitely many, and then construct the number. So P1 to Pn times 4 plus 1. And now all these, so any prime that divides this must be of the form 4p plus 1. However,
Not really. That's the major, like that you need to prove. So Euclid's proof says that general proof. I'm not saying modulo p. It's just like Euclid's proof for infinitely many primes says that infinitely many primes with no condition, like it could be 3 modulo 4, it could be 1 modulo 4, we don't care right now. So if that is the
that
case,
is just product of primes plus
yeah,
1.
exactly, product of primes plus 1. So you let there are just are finitely many primes, then you just take the product, add 1 to it, then you know that every element should be like this is not equal to 1. So that means there should be a prime which divides this element, this new element. But p1 to pr cannot be that prime, because if you divide by p1 to pr any element or any prime out of these p1 to pr, then you will get just 1. So it cannot be a divisor of m. So there will exist some other prime which will divide it. So that's the proof of that's the Euclid's proof for infinitely many primes. Now what could happen, as you were saying, the question now becomes like how many are there infinitely many primes, uh, uh, 3 modulo 4 or 1 modulo 4, like with the condition that infinitely many primes such that not such that satisfying 1 modulo satisfying 1 modulo 4. So okay, let use some space. So what I want to say, so primes could be like that. Primes either could be of primes could be of the form 3 modulo 4 or 1 modulo 4. Do you agree? So it cannot be 1. So when you divide by 4, either it will the remainder will be 3 or 1, because it cannot give
Yes.
2. right? If it is 2, then it cannot be a prime number, that has to be an even number. And 0 mod 4, again, that cannot be a prime number, it is divisible by 4. So it could be only of the form 3 mod 4 or 1 mod 4. So there is this interesting question. We have proved that by Euclid's proof, as we discussed, there are infinitely many primes of any type. Like we are not separating the cases 3 mod 4 or 1 mod 4. So the next question is like, how many primes, or maybe more precise, are there infinitely many primes of primes satisfying 3 mod 4, like the primes we are just considering which satisfy this condition 3 mod 4. That means, for example, 7 or maybe 7 11, I think, yeah, 11 or 3 mod 4, so 15, like this. So 7 11 15, like this. Are there any infinitely many primes of this kind also? Next question, are there any infinitely many primes satisfying 1 modulo 4? So these are two questions which you can think actually. So think about proving it using Euclid's proof. Use the Euclid's idea of proving a number of proving that there are infinitely many primes of both the types. But just think which proof is not very direct. Like one of them is a little bit trickier, which actually uses this part B2, so which I am going to prove now. So just think about that. Okay, so these are two interesting questions. Use Euclid's idea only, like this product plus one thing, or 3. You can add plus 3 or whatever if you want, but like this only. Then one of the proof will follow, but one of them will be trickier, which will use this part now, P2. We can discuss it next time, but it's a good exercise to do. Okay. Right, so where were we again? So p is not equal to 2 is a prime number, then again we have to deduce that the element -1 is a square in Zp if and only if p is equal to 1 mod 4. So to show there exists x belongs to, so actually this is maybe Zp, or what was it? Yeah, so there exists x belongs to Zp such that x square is equal to -1. So this is a quadratic residue. -1 is a quadratic residue. If and only if p is 1 mod 4. Okay, so we need to prove this. And p is given to be, p is not equal to 2. Of course, we are not talking about that. So, yeah. Okay, so how shall we proceed? So we can even use Wilson's theorem. We have proved it now. Okay, so at least tell me which direction is trivial, or which direction we can easily show. Okay, how about this? Assume that there
P
exists.
is congruent
Yeah.
to 1 mod 4. We can show that x square will be equal to -1.
Okay, how? Okay, I was doing other side, but anyway, we can do this also. Yeah. How shall we do that? So let's assume P is 1 mod 4. Then?
Oh, never mind.
Yeah.
Actually, give me 2 minutes, I think.
Okay. Actually, this other side is very direct, which let me explain that. So there exist. So we have there exist given. So given condition is x. There exists x belongs to Zp such that x square is equal to -1. And now ZP is again like okay, so anyway, so such that x square is equal to -1. Now what does this mean? This implies x raised to power 4 is equal to 1, right? We can write this. Now what will happen? Yeah, so what I was doing, yeah, so you know that if you take G to be ZP cross, so this is a cyclic group, multiplicative group anyway, right? And this x belongs to G. So and order of G is what? Order of G is equal to P minus 1, right? So this implies 4 divides P minus 1 by Lagrange's theorem, because this implies order of x is equal to 4. Because you know that x square is equal to -1, so x raised to power 4 is equal to 1, and there is no like 3, you do power 1, 2 or 4, 3, the order will be like the power that power will not be equal to 1, so order has to be 4. So by Lagrange's we have this condition. So 4 divides P minus 1. What does this mean? P is equal to 1 mod 4. Or maybe I can write better. So this implies P minus 1 is equal to 0 mod 4. And that will imply that this is equal to 1 mod 4. Yeah.
Yes.
Yeah. So this was this. Yeah, let's prove the other side. You want to try?
Yes. Want to try.
Okay, should I leave this part? Or even I can explain, because it was also in lectures a bit. So, okay, I'll just explain. Okay, so P is given to be 1 modulo 4. So, what we will do, we need to find an x such that x square is equal to -1. So, what we can do, we can construct such element x. So, let's do this. From Wilson's theorem, what do we know? From Wilson's, P minus 1 factorial is equal to -1 mod 4. Sorry, mod P. Right? We have this condition. So let's use this. So what is P minus 1 factorial? Let's write it down. What is this? 1, 2 into up to and so on. P minus 1 by 2. Next number will be what? P plus 1 by 2. Up to and so on. This will be P minus 1. It will be like this. So there will be this middle element P minus 1 by 2. Next will be just plus 1 of this. So plus 1 of this is what? P minus 1 plus 2 by 2, which is P plus 1 by 2. Right? So next number will be P plus 1 by 2, and next is P plus 3 by 2, and so on. So this factorial can be written in this form. Right? So what we are saying, let's write this. So actually note that this part you can again club it and this factorial. P minus 1 by 2 is well defined, because P is not equal to 2 and P is a prime number. So it has to be odd prime. So minus 1 by 2 makes sense. This will be an integer. Now, what can you write this to be? So P plus, so I'm doing this, P minus 1 minus, okay. So this is a part I'm writing for this one, okay. So this is P minus 1 by 2. Can you write like this? Because what will it be? 2P minus P plus 1 by 2. That is equal to P plus 1 by 2. So can I write like this? P minus 1 by 2. Is that okay?
Yes.
Okay. So even the next one element before that, what will it be? This is P minus 2, even P minus 3, P minus 4. It will be like this. Right? So what we can do here in this part, we have this. So we have P minus 1 by 2 factorial. So if we go mod p, then this is p minus 1 factorial. This is equal to, if we go mod p, then this mod p, like mod p, when you go mod p, this p will be just, you can assume it to be 0, and there will be minus at every place. So it's like mod p, what will it be? P minus 1 by 2 up to and so on, the descending product. This into minus 1 raised to power, there will be minus at every part, in every part. So how many will it be? P minus 1 by 2, because this is starting with 1, 2, 3 up to and so on. P minus 1 by 2. So this, so mod p, if you go mod p, then this first p will be just 0. Then you have this minus sign, which you just club it separately, and you take this positive thing inside. Is that okay, this step?
Yes.
Okay, great. So when you go mod p, this will be equal to minus 1 because of Wilson's theorem. So this will be equal to Wilson's, will be, because you are in mod p, so you can write minus 1. And what will it be? So this is again p minus 1 factorial, so you can write it to be square of this, and you have this minus 1 raised to power p minus 1 by 2. But what you have in this condition, that p is equal to, given that we already know p is 1 mod 4, because we have assumed that we are proving this side. We already have p is equal to 1 mod 4. This implies p minus 1 is equal to 0 mod 4. And this implies, what will it happen? This will be an even number, because mod 4 it is 0, so it is like when you just divide by 2, it will still be even. There will be a factor of 2 because it is divisible by 4. So you will get minus 1 is equal to p minus 1 by 2 factorial square, and from this part you will just get into 1. And that's why it is not true for 3 mod 4. When you do 3 mod 4, you will not get a even number, even power, so it will be just minus 1. And so minus 1 will get cancelled, so you will not really have any element. This is not the explanation to do that, but this will not work at least for 3 mod 4. So this will be equal to p minus 1 by 2 factorial square, and that's what we need. This element belongs to G. This implies there exists x is equal to p minus 1 factorial in G such that x square is equal to 1, which we require. Sorry, x square is equal to minus 1. So it's like there exists an element of order 4. Is that okay? Is that
Yes.
okay? Okay, great. Just try that prime number thing. It's interesting. You like it.
Ma'am, please bring down the page once, and this position, hold this position
Yeah.
slightly upper.
Okay.
Um,
This one or earlier?
just
Which part?
back page. No, sorry. Bring down.
You can tell me which part. I can just open that. Direct.
Or bring down. Yes. Okay, एक second.
So we just
हाँ,
write
ठीक है,
p.
हाँ.
Yeah. So we wrote p minus 1 factorial to be some like separate forms, and we just did a clever argument.
Okay.
I'll upload the notes anyway. Like I
Okay.
remember last time once I have not uploaded, but I'll do it today or tomorrow at most.
The previous note has not uploaded. You have.
Yeah. Last time once actually I was traveling, so I couldn't do it, but I'll do it.
I am not getting the email also.
Uh,
I have a question to ask
yeah.
regarding the previous day.
So okay. So
Okay. After that session, today's
yeah,
session.
sure. Okay. Yeah. Okay, so let's move to the next question. Let G be a non-trivial group. G is a non-trivial group, so it's like maybe not a 0. So it's not just the identity one. So this implies G is not just the identity group. Show the following statements are equivalent. So let's see. So what does this say? So first statement says, I'm just writing these statements for understanding. We need to prove that these statements are equivalent, first, second and third. First says, there is a proper subgroup of G which contains all other subgroups of G. So you have, there exists a proper subgroup K. So proper subgroup means this is not equal to G. So it's like, so this less than notation is for subgroup, which I use. If you want, I can write it down also. So this is for subgroup. Okay, so K is so first condition says there exists a proper subgroup of G, so which is not equal to G, which contains all other subgroups of G, such that for all H subgroup of G, which is again proper. Okay, so we should write this is again proper, just don't be confused by that, because K cannot contain H, K cannot contain G. So we are just talking about such that for all H subgroups of G, what am I writing? For all H proper subgroups of G, H is a sub, we have H is a subgroup of K. Okay, maybe equal. So what does this say? Other than G, so you know that G contains all the subgroups because it's these are the subgroups. So by the definition itself, these are subsets of G. But it is saying there exists a proper subgroup of G such that all the other subgroups, even K, all the subgroups of G, proper subgroups of G contains this K. So it's like a maximal subgroup. So if you think about like maximal ideal, like in ring, you know that there is a maximal ideal, there is no bigger one, but unique maximal ideal, we are saying, kind of that thing. So it's like K is maximal in the sense that all the subgroups of G which are not equal to G are the subgroups of K. Is that condition clear? We don't need to prove this. We have to prove the equivalence. If this is the condition, then second holds, then third holds. It's like that. I hope this statement is clear. Let me know if not. Okay. Second says G is a finite cyclic group. So G is finite, cyclic. G is cyclic. Group of prime order. So it's like, and order of G is equal to some prime power. So it is saying it is some prime power of like order is prime power. Third says G is finite. So G is again finite. Next, the set SG. So this calligraphic SG of subgroups, it's not calligraphic actually, so SG of subgroups of G is totally ordered with respect to the natural inclusion. So what does this say? If you consider all the subgroups of G, so this is set of subgroups of G, then so let's say this is equal to H1, H2 up to and so on, let's say HK. Okay, say then H1 is a subgroup of H2, something like that. We don't know this is the order or not, but there is some order. It could be like H2 is earlier or something. We have some conditions. So there exists an ordering, total ordering. It's not even partial. So we have total order on the subgroups of G. There's a chain we get. So even the last one will be G, and the starting one will be just identity. because we know that these will be the subgroups at least. Is that okay? These three statements. First says there exists some proper subgroup of G which contains all the proper subgroups of G. Second, if G is finite, G is a finite cyclic group of order p raised to power n, some prime power. Third is G is finite, and the set of subgroups of G are in total order. That means there exists a chain H1 to Hk such that H1 is contained in H2 up to n. So we have the inclusion only. So the condition says it's an inclusion. Okay. So can you give me an example of such a group? So actually we are anyway proving equivalence. So that means all the subgroups should be of this kind, second kind. Order of G is less than infinity, like it's finite, and G is cyclic, and order of G is p raised to power n. So general example. So it should be finite. Anyway, if whatever example we will choose, it has to be of prime power and it has to be cyclic. So for example, you just take
P to the
Z4.
power something, order of the group P to the power something.
Yeah, exactly. So for example, let's take this. So this is a cyclic group of 4 elements, right? So this is like 0, 1, 2, 3, and the operation is mod 4. So now so for example, first part, can you tell me which k I should choose in this case? So what are all the subgroups? So let's write what is SG. SG is, so subgroups will be like 0, one subgroup we already
0, 2, and
yeah,
the entire group itself.
exactly. So we have 0, 1, the full subgroup. Because if 2 comes into the picture, like if 2 comes in as the element of the subgroup, then full, because 2 generates it, so it has to be the full group. So we have just 3 subgroups here. So what can we choose as k? So this is the only choice we can take, because we cannot choose the full group, so this G is not allowed. So you can just choose 0, 2, and then you know that all the proper subgroups, so all the proper subgroups means this and this, these are 2 proper subgroups that are contained in K. So the condition is satisfied. You can try with other examples also, for example Z8, or some power of prime, so let's say 9, 3 raised to power 2. So you can try that. Okay, let's try to prove this condition, like these equivalences. So okay, so which one should I try? For example, let's say second to third, this part, because second is a very big condition which actually characterizes all such groups. So that means that is the stronger one. Anyway, any of these are stronger, but this gives a precise definition. So if you try second one, then can you tell me why third is true?
Because so if the number of elements in the group is of the form p par n, then the order of every element will be p par k, where k
order,
is between
right.
1 to n.
Right.
So from there, so if I take, for example, so the first one, which will be order of element 1, that is obviously going to be identity. If I take p, then it's going to be p minus 1 elements, and p square, that is going to be, so like this you can construct for each power of p, and you can see that obviously since every element in the previous group has an order that divides the next group, all the elements in the previous group will be contained in the next group.
Okay, so you are saying order divides, that does not mean that. If order divides, that does not mean that it will be contained in the bigger one. So what he is saying, so let me you, this is okay, but yeah, we need some more argument. So as you said, any element of G is what? So it's like whatever element you take, A belongs to G, implies there will be some power of p raised to power r, which is like r is less than n, because you know that order divides order of any element will divide order of the group because of Lagrange's theorem. So it has to be some power of p, so that because the
No,
divide,
okay.
yeah.
Alternatively, let's say since G is cyclic, I can say it is generated by A,
Yeah.
and uh, and now if I take so I know the order of A is going to be p raised to n.
Yeah.
Now if I'm trying to find every other element, it has to be something that divides p raised to n.
Right. Order
So
order will divide, yeah.
so that will be p raised to k.
Right.
So now I can see that if I take any group which has a larger order, then the elements of the previous group will be contained in that
There is
by this
one
definition.
argument. Yeah. This by what?
By this definition of the cyclic group, it's going to be contained in the
Uh, one thing you are missing. So there's this claim, if you so okay, let me explain one more thing. So what we have, as he said, all the elements of G will have some order p raised to power something like less than n or equal to n, but it will be some power of p, order of any element of G, right? So let me not confuse you all with this A. So we have this thing, and what are any subgroup of G will look like what? Subgroup of G. Uh, okay, one more thing. So actually I have written one exercise earlier which you can use here. So we have written this part. If G is a finite cyclic group of order n, then for each divisor there are exactly 5D elements of order D in G. So in our case, using this exercise, which you can prove easily, just try it out, it's just group theory. So G is equal to, so any element, so if B belongs to G, then this implies order of B is some p raised to power r, let's say, where r is less than or equal to n, or even this, yeah. So this will be this condition. So order of B is equal to p raised to power r, and number of elements of order D of order p raised to power in, yeah, it's a separate statement, I don't know, and number of elements of order p raised to power in G is phi of p raised to power r, right? Now I am claiming something. Okay, should I add one more thing? So okay, so any subgroup, okay, one more thing, from Lagrange's theorem again, if H is a subgroup of
no.
G.
So over here we can say that, right? Like summation of phi of p raised to r.
Yeah,
P raised to
exactly.
I, where I goes from 0
Yeah.
to
N.
r will be equal to I. Okay, fine. N will be equal
Okay,
to
yeah.
phi of p raised, p raised to n.
Yeah, exactly, p raised to power n.
So from this I can conclude that.
You are, whatever you are saying, yeah, just you can actually say this is unique. That's the word maybe you are looking for. Yeah. So if H is a subgroup of G, then by Lagrange theorem, okay, sorry, so Lagrange theorem, order of H, so order of H means cardinality of H, will be equal to some power of P, okay, and if I say that this is generated by A, then H will be generated by some element. To be precise, you can say p raised to power n, so it will be n by r. Oh no, not this. A raised to power p raised to power n minus r. So you can even see that. So any subgroup of a cyclic group will be generated by some element, like which with that will be again cyclic. And now in any cyclic group, the number of elements will be exactly number of elements of order p raised to power in G will be phi of p raised to power r. Now you have these many elements only, so if you consider H, so you can, so the condition says this implies and since H is cyclic, number of elements in H of order p raised to power r will be equal to phi of p raised to power r, right? Now you know that G also have 5 p raised to power r elements and a of order p raised to power r, and H which is of cardinality p raised to power r also has phi of p raised to power r elements. So you don't have, and if there exists any H dash of subgroup of G such that cardinality of H dash is again p raised to power r, if there exists any other subgroup of same order of p raised to power r, then it already uses these phi raised to power pr. So there is one more thing. If you take that element, if you consider any of these elements, then again you will get H dash to be same as H, because these generate the subgroup, this generate the subgroup H dash, so it will be the same one, same. So this implies H dash is equal to H, because we don't have any choice. G also contains phi of p raised to power r elements of order p raised to power r, and any subgroup H will also need phi p raised to power r elements. So you can only make one subgroup. That's the whole thing. That's the upshot of this part. So in any cyclic subgroup, so this is again a general statement, cyclic group, there exist exactly, sorry, not exactly, you can just write, there exists unique subgroup of order, any divisor of order equal to or better. So in any subgroup, any cyclic group G of order n, there exists unique subgroup of order of order D which divides n. So for any divisor, you know that every subgroup will divide the subgroup order. The order of the subgroup will divide n, first thing, and for every divisor, for each divisor, you will get only one subgroup. That is not true for any other like any non-cyclic group. Even you can, this is a if and only if condition. Even if you prove that there are unique subgroups of order D, which are the divisors of n, then G will be cyclic. You can even prove the other side also. So this is a if and only if condition. So this means, so using this, what will we have? We have, so this implies G has unique subgroups of order p raised to power r for r is from 0 to n, right? So this will have unique subgroups. So Now what does this imply? Now you know that if you consider the subgroup of order p raised to power n minus 1, so if you start with G, then you consider a subgroup of order, so uh, I don't know, like I just take some different subscript, so that is HK, so that is of order p raised to power n minus 1. Next you will have k minus 1. Even I can take n, so n or n minus 1, so this is n minus 1 and this is n hn, which is equal to this of order p raised to power n minus 1. This is of order p raised to power n minus 2, and up to and so on, because you have unique subgroups of every order. These are unique subgroups, but why it has to be in the inclusion? So even I have said in subgroups, even these are not with the inclusion as a set, but these are subgroups also, because you have you have unique subgroup. Now hn minus 1, which is a subgroup of order p raised to power n minus 1, so this will have this itself is a cyclic subgroup, so it will have some subgroup of order p raised to power n minus 2. Now this also have this, and G also have a subgroup of that order, then it has to be same, because G cannot have two subgroups of same order. So that means this chain is justified, and you go on with, let's say, 0, which is identity. Is that clear? So there are some statement like these are good properties of cyclic groups that you can use and directly show this. So we use this part that it has unique subgroup of every order. Okay, so this was our second implies third. Now third implies first. Is this okay? So I'm proving third implies first. So we have,
Ma'am,
yeah.
you can also do third implies second also, right?
How?
Because we'll say that if every group is a proper subgroup of every sub, like if there's total ordering, then basically, and we know that all the subgroups have to have an order, like they have a division, like so say H1 and H2 are there, and H1 is contained in H2,
Yeah.
then the order of H1 has to divide order of H2.
Yeah, it could be equal
And
also. There's one thing.
yeah, it could be equal also. And we and so if I write for everything, then I could finally conclude that if it's of any other, like if there are at least two primes, then there could exist two such final subgroups of, so if it's say for example p raised to n and q raised to r, then finally there could be
1 second. It could be something else, like p into q also. We don't know.
that's why I said p raised to n, q raised to r,
Okay.
or how many ever, right? But my
Let's
point
say,
is, yeah, let's just take the simple case for now. And so there could exist a subgroup of order p, and there could exist a subgroup of order q, and between these two you cannot have a total order. So if there has to be a total order, there has to be only one prime.
Yeah. So right. So also, how will you say that this is cyclic?
Every finite abelian group is cyclic.
No. Z2 cross Z2.
Oh, right.
Yeah, that will need a argument, but yeah, I got it. So if you take so again you are I think if I naming it correctly, maybe Seller's first theorem or Cayley's theorem, that if a prime divides the group, the order of the group, then
Tyler's theorem, Cauchy's theorem.
Cauchy's theorem. Thank you. Yeah. Thank you. Yeah. So if P divides the order of group, then G will have an element of that prime number. So
Huh.
it is true for the prime number. It is not true for some square of prime, let's say, because Z2.
Yeah, that's why I use P and Q itself.
Yeah. So yeah, exactly. Yeah, I got it. But now you just need an argument for so it has ordered some prime power, but you will need an argument for uh, yeah for cyclicity of this. Okay, so I'm just proving it as in a cycle. So you can try it out. So of course this will follow some with some argument. But, I have planned to do. So second implies third. Now can you tell me why third implies first?
When we take the larger one, which is not a
Ma'am, what is totally ordered and partially ordered and totally ordered?
So we
This
yeah.
is
So
here
this
you are writing H1 subset of H2. This is partially ordered.
no. The
No, it's
partial
totally.
order means there may be two chains. So there could be elements which are not comparable. So totally order means every element is comparable to other. That's the Zohn's lemma for third implies first. Do we need Zohn's lemma even? Oh, okay. So G is finite, so we don't need Zohn's lemma in that case, maybe, because if you just say G is finite, so there is this finite chain, and then there's a finite chain, so you just pick the highest one, as you were saying. Maybe I don't know. I think. Uh, so, I think Anjani was saying. Yeah, so maybe so you have this chain, so you just pick the highest one. So hk minus 1 I can pick. So hk minus 1, so you just pick that hk minus 1, and now you know that this is a proper subgroup because we have not taken G to be our element to. So hk minus 1, let's take this to be our k for the first part, and then you know that all the subgroups are subgroups of k, right? All the subgroups of G, proper subgroups of G, because these are behind hk minus 1. So these are all subgroups of k, and we are done. So this says that there exists some k which we have picked it to be hk minus 1, or maybe any other quantifier you want to use. I used small k, which might be bad, but this is big K, this is different. Is that okay? The third implies first is direct. So main thing is to prove first implies second. So let's try to prove that, because we have proved second implies third implies first. So if we prove first implies second, then we are done, right? Cycle we have made. Okay, so we have given there is some k which is where H is a like where all the subgroups of proper subgroups of G are subgroups of k. So let's try to prove this first implies second. So let's try to do it. Okay, so there exists k, given condition is there exists k subgroup of G such that for all H subgroup of, so this is proper, again proper subgroups of G, we have H is a subgroup. Now I will not say proper here because I can choose H to be K, because that is also a proper subgroup, so that's okay. Okay, so now we need to prove that G is cyclic, G is finite first. So we are even don't know that G is finite, so we have to prove that also. So okay, so we need to prove G is finite. To show finite, G is cyclic, and order of G is some prime power. Okay, so I'm proving cyclic first, so let's try to do this. We have okay, since K is a proper subgroup of G, this implies there exists some A belongs to G minus K. So there exists some element in G which is not in K. Okay, now take Yeah.
A compose
Uh,
is generate.
just take, yeah, generated by A. Okay, then this since this is not a subgroup of K, because A does not belong to K, so this cannot be a subgroup of K. This implies, by the given condition, that uh, this has to be, A has to be G, because this has to be a proper subgroup, so this has to be the whole subgroup then, because we know that if K is K is we have K is such that it is for every proper subgroup of G, we have H is a subgroup of K also, right?
Otherwise, it must be same group, the whole group given.
Yeah, the other condition, it is not proper, so it
Hmm.
has to be the condition that
So it is cyclic. So.
yeah, so this is cyclic, so we have cyclicity from here. First thing, now we need to prove that this is not
Yes.
infinite. So yeah, this is finite, so G is cyclic. So can you tell me how shall I do that? So G is cyclic, we know this, infinite cyclic group.
Hmm.
So K
You
has to
mean
be, yeah,
contradictory? We first let us give a infinite cyclic group with
yeah. So let's assume G is infinite cyclic group, and let's say G is generated by A, then K will be what? K will be some power of A raised to power S, like generated by A raised to power S. One more thing, where S is not equal to 1, and not even minus 1. So, yeah.
infinite cyclic group has two generated.
Right. So even you can think this isomorphism. G is isomorphic to Z plus, right?
Yes. Hmm.
All the infinite cyclic groups are isomorphic to this Z plus. Now, can you see? Does Z
Yeah,
plus has this
2Z
property?
and 3Z are
Yeah, its subgroups are of the form
NZ, NZ.
nz or 0. So of course 0 cannot be K, so that cannot be a thing. But if you pick any nz, can you say that all the subgroups will be contained here?
it's partial.
This is not possible, right?
Yeah, yeah.
So this cannot be the case. Yeah.
Please repeat. Uh,
Yeah,
if I
so
take
right, so in nz, so I can think of in z plus, even you can think here also, but even that is familiar thing. So if G has some K of G has some subgroup K which satisfies this condition, there exists K such that all the subgroups are subgroups of K, all the proper subgroups of G are subgroups of K, then if we think of, we are trying to find whether this is possible or not, right? So all the subgroups of Z plus looks like nz or 0, right, where n belongs to some natural number, excluding 0 for now maybe, or maybe you can write 0 included here. But yeah, these will be all. So of course you cannot take n to be plus 1 or minus 1 for K, so K has to be some mz, let's say, or maybe nz, such that n is not equal to plus 1 or minus 1. So what does this mean? Whatever n you will choose, can you find, so the question is, can you find such a n such that all the subgroups will be contained?
um, all the subgroup contents.
Actually, firstly you have to pick a prime, because that is the bigger one, any
Bigger one.
prime. But if you pick any
Yeah,
prime, can you make
if the
sure?
primes are distinct, then there will not be any intersect. There will be some amount that will be left out.
Exactly, so this cannot be possible in this case,
Yes.
right?
Yes.
So firstly n has to be prime, because if it is not prime, then anyway we are losing some information. For example, it is, let's say, 6z, then we don't have 2z, 2 here, 4 here, so
Yes.
we don't
Clearly, yeah.
have 2z. So firstly n has to be prime, but if you pick any prime, can you make sure that other primes are there? No, right? If
Yes,
you say this is 2z, then 3 does not belong to, so
belongs to that.
yeah, 3z is not a subgroup of 2z, or any prime, you take any prime and any q. So this is not possible because we have this Bezos theorem that q and p, or maybe you can just say GCD is 1. So this cannot be the case, right?
Yes.
So infinite is also we cannot take. So we have cyclic, we have finite group. Now we need to prove that its order is p raised to power n, right? So let's just complete this. Okay, so p raised to power n. So again, as you were saying earlier, you have this p into q thing. Okay. Better. Let's. This is equal to some p raised to power. Okay, we don't know that. So order of g. Let order of g is equal to some p1 raised to power r1 up to and so on p m raised to power rn. I've just taken random numbers where pi's are distinct p1 to pm are distinct primes, right? And let's say r1 to rn belongs to, so I have used 0 also, so maybe I don't know whichever notation you like. So 0 is there. Okay. Oh, sorry, no, I should not say 0 is there. Okay, so we or maybe n minus 0, whether it is there or not, but this makes sense. So we have taken prime powers, we have separated the prime powers here. Now let's okay, since g is cyclic and we have this condition also, g is generated by a, then order of a is equal to p1 raised to power r1 up to and so on pm raised to power rn. Then a raised to power p raised to power r1 will have order p2 raised to power r2 up to and so on pm raised to power rn. Is that okay? So I have just taken this power. Then if I a raised to power p raised to power r1, if I power it to this part, then we will get 1, and then and this will be a generator because there is no
Order of a to the power a raised to the power p to the power r1. You can say it would be say that order must be divided that thing. How can you exactly say that it would be equal to p to the power raised?
okay. Yeah, it will divide, right? So okay, how shall I say, one thing, if it is less than that, right? So for example, let's say if it is p raised to power r1 and it is less than some quantity p raised to power m raised to power rn, let's say not q, some b, let's say just a number, let's say this is equal to 1. Okay, we are proof, of course we know that a raised to power p raised to power r1, if we power it with this quantity, then we will get 1 because we know the condition from a. But if we so as you asked, so it will, so order will divide this part, but how can we say that this is exactly equal? So what we have to prove, that if we just if we reduce it to, like, if it is less than that, then it the power, if we power it, then we will not get 1, right? So
Yes.
let's do minus b. Then what does this mean? What will happen in power? This will get multiplied and you will get this minus p raised to power r1 into b, right? So this inner power will just will get just multiplied with this, then this will be 1. But this is a contradiction because a exactly has this order, so b has to be 0.
Yes.
This implies b has to be 0. So we can say that this will have this order. Okay. Also, order of a raised to power p raised to power. Now you take p. Oh, sorry. This is p1. Okay. Yeah. P1. Now you take p2 raised to power r2, a raised to power pm raised to power rm. What will be the order of this element? Okay, sorry. It's just in powers. So a raised to power p1 raised to power r1 up to and so on, pm raised to power rm. Or let's say 2. So I have taken a raised to power the remaining part. Now this will have order p1 raised to power r1. Right? Same argument. Now what I did, I separated this first one, p1 raised to power r1. I have just taken the remaining part. Even you can do it with induction and just take two PIs. That will also be
Yes.
fine. But let's do as we started like this. So we have these two conditions. Now what will happen? Now we my claim is, if this is the case, so if there exists such PIs, so we at least say that m is greater than or equal to 2. So at least we are taking 2. We need to find a contradiction. So my claim is this so whatever k is, so k is a subgroup of our choice of this choice. So because this is a given statement, so there exists some k. So consider this k. Since we have this case such that for all subgroups of proper subgroups of G, such we have k H is a proper not proper, H is a subgroup of k. Right, we have this condition. This implies, now you know that these two elements, we have this order. We know that p1 raised to power r1, this this is a subgroup, so this will be in k also. If you take a p2 raised to power r2, even I don't need earlier statement, but anyway, so this implies, okay, let me say this. So this is also in k. Okay, so what I mean to say, you take these elements, a raised to power p1 raised to power r1, and the other one is a raised to power p2 raised to power r2 up to and so on, pm raised to power rm. Then if you consider the subgroup generated by these two elements, then it will be in k, because these are proper, we already know, because orders of these elements are strictly less than order of G, which is strictly less than order of G. And we know that if that is the case, even we define order to be order of any element to be the subgroup generated by the cardinality of the subgroup generated by that element. Even that definition we are using in lectures. So even you can think of in this way. So order is strictly less than order of G. So strictly less than means not equal, right? So that means these are proper subgroups. So these has to be contained in K from the condition. So this implies a raised to power p1 raised to power r1 and a raised to power p2 raised to power r2. So these two element has to belong to K. These two elements should be in K. And now this implies, since this is a subgroup, this is a group, so the multiplication has to be there. One more thing, I am doing something. So p1 raised to power r1.
Ma'am, or we can say that order of the group of the order of the subgroup must divide order of k.
Yeah.
So from there we can say that for the first case, p2 r2 so on up to pm rm must divide order of k, and for the second condition p1 r1 must divide order of k. And since these are primes, the only way this is
Right.
possible is the entire thing will divide the order of k, which means
nice
that k has to
explanation.
be equal to g.
Yeah, thank you. Yeah, this is, of course, this is a good way to say that. This implies p1 raised to power r1 divides order of k. So order of k means this, and this implies p2 raised to power r2 up to and so on.
Other way around, right?
Sorry?
Order of that will be p2 r2 up to pm rm, right?
No, this will divide order of k, right?
No, if you scroll up a bit.
Right.
Huh.
Okay, yeah, I got your point. Yeah, not the element, it's the order. So
Yeah.
order of this subgroup is p2 raised to power r2 up to and so on p m raised to power rn. This will divide order of k, and also this implies p1 raised to power r1 will divide order of k. And since these are primes, these are distinct primes, the GCD is 1, so this implies this whole thing from 1 to m will divide order of k. But that means this has to be equal, because this could be the maximum possible thing, but then this means g is equal to k is equal to g. Yeah, this is a nice argument. Actually, I was going to do this one. So since GCD of this and p2 raised to power r2 up to and so on pm raised to power rm is 1, yeah, there is no dash here. Since GCD is 1, this implies there will be some a, not a, s and t maybe. So s plus t p2
And
raised to,
Bayes' identity.
yeah, this will be equal to 1. So I thought of explaining like this, but yeah, this is better. So if you take this and you have this thing, so this implies t p2 raised to power r2 up to and so on pm raised to power rn. This will belong to k, but this quantity is 1. So a will belong to k, that means g is there. Which is a contradiction. Yeah, but this is a nice argument. Thank you. Yeah, so I'll stop here.